All right. Well, welcome back, folks. I hope things are going well for you. I haven't seen many of you. I haven't actually seen anybody after school. So what I may do then is I may just call for a live class next week where we will actually meet on Zoom here in a live session where I can go over the material with you. So it'll be a live presentation. I will let you know when that presentation will be. This way, then I just get a chance to see how you guys are doing, interact with you folks as well. But like I said, please make sure you stop by and get any questions you have about the material as we move forward with this. And I know that this is not what you signed up for. My hope was that we could do more hands-on stuff, but unfortunately, with the kinematic stuff here, there's not many hands-on stuff that you can do. I will try to find a fit lab that will be appropriate for this particular material. I think once we get to the section on acceleration, I think there is a fit lab that is available for us, and I'll ask you to do that. But outside of that, I am trying to put together a build for a trebuchet or a catapult that I think you could possibly build, but that won't come until towards the end of this unit when we start talking about the two-dimensional motion and projectile motion. Okay, so that's my hope. I'm going to see. I'm going to take a look at the build there, see if it's going to be something that we can do or you can do in your own home. And essentially, the idea then is that you would build it at home. You would record a video of your catapult working, and then you'll submit that. Okay, but let me put that together for you. Let me put that the build there together for you, and then I'll assign it hopefully once we get to the section on projectile motion, which is probably towards the end of next week, if not the following week. Okay, but in the meantime, we're just going to be interacting through our our video here. And so, like I said, I haven't heard from anybody. And so what I think I'm going to do is I'm going to probably call a live session. So we'll have a live meeting sometime next week, and I'll make that announcement for you. And that way we'll be able to interact a little bit more. Okay. All right. So let's go ahead then. Let's continue on where we left off with yesterday. So I asked you to do this problem here, and I was able, and then we were able to plot this motion here. Okay? We were able to show then how this, what these two objects are doing. And so we drew this picture yesterday. I drew this for you, and then I asked you then to finish solving this problem, to work out this problem here. And so that's what I would like to do at this moment, and be able to work out this problem with you and give you a chance to write this down on your own paper. Okay? So we have two objects moving. So make sure you understand that what we've done here is that we're using this equation. So what we're essentially doing is that we were able to obtain this equation right here. We were able to obtain this equation from the plot of a position time graph. So we took a position time graph. Okay. So position time graph. And in a position time graph, remember what we're doing is we are plotting the motion of an object. It's changed in its position for time. And so on a position time graph then, remember, on a position time graph, positions plotted along the y-axis, and time is plotted along the x-axis. We saw then that if we take the slope of that line, we have then the change in y, which is the rise, which is the change in position, over the run, the change in x, which is going to be the change in time. Okay? And so we saw then that with this particular unit, with the analysis of that slope then gives us velocity. Okay? That slope then is the velocity of an object, and we define velocity as a change in time, a change in position as an object moves through time. And so that's where this formula came from. And that's what we have to be able to get used to. We have to be able to take information from a graph, and here we worked with a very simple graph, take information from a graph and change it into an equation form, find an equation that will relay the same information here. Why? Because we can take that formula then and use that to make predictions about what will happen. Okay? So for example, we know the velocity, we know how fast objects are moving, which is, we do know. So in both cases here, we know how fast both cars are moving. Okay? If we know how far they move, how far they have moved, which in both cases we do as well, okay, we can then go ahead and calculate for the, we can go ahead and calculate then, sorry, for the, let me erase this really quick. We can go ahead, which, I'm sorry, which we do here. We can go ahead and calculate for how much time it took them, excuse me, to complete this trip here. And that's the benefit of having these formulas. We don't have to deal with a clunky graph. We don't have to be able to interpret it. We can just we're just able to plug in numbers here and get the answer that we need. So that's the power of formulas. And that's why so much of the descriptions that are given in physics are given in the form of formulas. So formulas are vitally important. Okay? All right, so with that said, let's go ahead then, and let's go ahead and calculate. Let me go ahead and write this really quickly for everybody. Okay. Go ahead then and let's calculate for the time, okay, and interpret. Okay, all right. So plugging in our values here. Okay, so plugging in our values, the distance traveled by car B. The distance traveled by car B is 50 kilometers. It travels at a rate of 100 kilometers per hour. So it's going to plug that in. That's going to be 50 kilometers at a rate of 100 kilometers per hour. And so the time car A takes to move 50 kilometers, which is from the school to the beach here, is going to be half an hour. That's the time interval. Okay, that's the time interval. That's how long it takes the car to go from school to the beach, which is the total distance of 50 kilometers. Let's go ahead and do the same thing for car A. Car A, remember, we were told starts 10 kilometers closer to the beach. It's at the store. That's 10 kilometers closer to the beach. So it only has to travel a distance of 40 kilometers. Okay? But it moves at a rate of 40 kilometers per hour. And so the time it takes to cover this distance is 1 hour. Okay. All right. So what we've solved for here is the time interval. This change in time represents the time interval. Okay. And so again, it takes half an hour for the car here, for car B to go from school to the beach. It takes an hour for for car A to go from the store to the beach. Okay. But that's not what they're asking you. They're asking us here at what time do both cars arrive? Okay. Well, let's consider this here. We were told then that car B starts at 12:30. Doesn't leave until 12:30. So car B leaves a little bit after car A. Okay, car B leaves a little bit after car A, but it takes only half an hour to get to the beach. And so therefore, at half an hour later will be 1 p.m. So car A arrives at 1 p.m. That's what they want you to solve for. Okay? And so with car A, then they're asking the same thing. If car A leaves at 12, leaves earlier, but it takes an hour to get to the beach, the car A then will get to the beach also at 1 p.m. So they will arrive at the beach at the same time. And these are the answers that they want you to get from this problem. Okay. All right. Hopefully everyone's able to get that okay. Hopefully you're able to graph this information too. And I'd be interested to see how you would plot this motion on a position time graph. Okay, how would you plot the motion of both these cars on a position time graph? And I think it would be informative for us to do that, but I'll let you do that on your own. Okay, and again, I'll finish up. I'm almost done with the packet of practice problems that you'll have to do for this to give you some practice with kinematics here. I'll post that for you on Monday, and then you can start practicing this. But like I said, hopefully you can draw the position time graph to represent the motion of both of these cars in one dimension. Okay. All right, but go ahead and try that. But we do have to continue on then. Okay, so let's continue on and let's take a look at where what we have here. Okay. All right, so we can represent graphically the position of a car relative to time. Okay, we can obtain the velocity. We said then the velocity then is just the slope of the line of that particular graph. The problem with that representation, and unfortunately this is a very huge problem, is that it oversimplifies the motion of an object. So for example, just think about this here. When you walk, if you walk upon, let's say you walk around your block, okay, you walk around the block or you walk to school, you're not going at the same rate. You're not moving at the same speed the whole trip to school, whether you're walking or driving. Sometimes you slow up, you slow down, other times you speed up, and other times you have to stop. And so when you plot that motion, then we have to be able to consider then your overall velocity. So the overall velocity is what we call the average velocity is going to be a straight line. Okay, so we try to find the average velocity. We're just going to take the final position, the initial position, and divide that by the time change that occurs there. Okay, but like I said, the objects do not move in a constant way as we have represented here. Okay, so on a position time graph here, the straight line here represents an object that's moving and it never changes its speed. The slope here from 0 seconds all the way to 38 seconds here, the speed stays constant. And objects over a very small time frame, over very short distances, over a very small time interval, will move at a constant velocity. But when you talk about objects that are moving in real life, they do not move at a constant velocity. And this is probably more accurate representation of how objects do move. So we interpreted this graph already before, and this is a graph you should be familiar with. Okay? An object starts at a position away from 0, so our arbitrary 0 point, starts to move away, and then he starts to slows down, and then stops. Okay? So make sure you understand that. Remember, when we interpret this graph here, at this point, at point B, the object stops. Now, every object known to us, has to slow down before it stops. It can't stop on a dime. Nothing is able to do that. Okay, right. So if you notice here, that's why this curve starts to generally taper. It starts to taper, and as you notice here, it starts to taper off and it levels out right here, which means then if we were to plot these points here, we plot the points here, you're going to see then that there's going to be eventual slowing of the object. And we're going to see how we calculate for that in just a moment. Okay. And then what happens is the object stops and then it starts to move again. It starts to move back towards the origin here. And if you notice between point B and point D here, that's roughly a straight line. So at this point here, he moves at a constant velocity all the way actually down to E. Now down here, understand this, down here between point D and point E, this object has a negative velocity, but that does not mean he slows down. A negative velocity just means in the direction the object is moving in. It does not mean it's slowing down. When we start talking about acceleration in just a moment, you're going to see how you can determine how an object is speeding up or slowing down. But according to this graph, or on a position time graph, the object has constant velocity. It doesn't speed up or slow down roughly between point B and point E. Because if you were to connect a line between point B and point D, it's going to be roughly a straight line right here. And with that said then, and let's go and take a look at that. Okay, so if you take a look at the position between roughly point B and point E right there, you have roughly a straight line. That slope is a straight line, and so therefore the velocity, and I'll increase the size here for you, the velocity then is going to be a constant velocity, okay? All right. However, if you notice here, when you get to point E and point F, the velocity then starts to change. For those of you who've had physics before, or if you're having physics now, or if you're taking calculus, you know then that we can calculate then for the instantaneous velocity. That is, what if we wanted to know, and so let's consider this here. If we wanted to know the speed that the object is moving at 10 seconds. At that moment in time, the object has a velocity of 0 meters per second. Okay? The question then is, what is the velocity of the object as it moves? Let's say let's not do that point yet. Okay? What's the velocity of the object at this point, right here, as it starts to slow down? Can we find that instantaneous velocity? So what we're asking here then is, what is the speed right at around, let's say 5 seconds. So we trace this line down. So we trace this line down here. Okay, let's go do this. We are basically asking then at this point in time, okay, so at that moment in time, which is roughly about what, 5 seconds? Okay, at that moment in time, how fast is the object moving? So velocity at 5 seconds. Okay, what can that be? Okay. Well, that is a question that's a little bit more difficult to answer. We can answer it fairly easily with physics. And so let's go ahead and if you've had physics, you would be able to answer this question. We can answer that question fairly easily by taking a limit. Okay, we can calculate for the limit here. I'm not going to do this, go over this in too much detail because most of us have not had physics, but the idea behind this equation then is that if we take, for those of you who are familiar with limits, then this discussion is for you. If not, then don't worry about it. Okay? So what we're doing here is we're saying then that if we take this value here and we make that time interval successfully smaller and smaller and smaller time intervals, okay, we can, that without getting to zero now, so the limit here as delta t approaches zero without being zero, because obviously if delta t is zero, you have an undefined fraction, doesn't work. But as the time interval gets smaller and smaller and smaller, okay, what we'll be able to find then is the instantaneous speed at that particular moment, at a single moment in time. Okay? Remember, this is a range of time, okay, range of time from beginning to end. But if we make that time interval smaller and smaller and smaller, we get to an instantaneous point. And so with that said, then when that gets to almost before zero, we have an instant in time. That's the velocity. That is how we calculate for, that's how we would calculate for the instantaneous velocity using a little bit of calculus, but it's a fairly simple calculation if you have taken calculus before. Okay. But for the rest of us, though, who have not taken calculus, how are we supposed to find that instantaneous velocity? Okay? Well, we can find that velocity, that single moment in time, the speed at that single moment in time, using a position time graph. And we can obtain it from the graph. And let's take a look at how we do that. Okay. All right. So the graph then, if we take a what's called a line that is tangent to a point, and this is a little bit more more algebra. I would argue algebra 2. I don't think I think that's where you learn it. You can correct me if I'm wrong in this one, but that's where you learn about tangent lines. And so what is a tangent line? Let me go ahead and draw that for you really quickly. If you can imagine then that there's a line that intersects exactly at that point. Okay, so a line that intersects exactly at that point. Let me go ahead and draw that line for you. Okay. There is a, for a single point on this curve here, there will be a line, a single line that intersects at that particular point. That is what's known. That is what's known as a tangent line. So this is your tangent line. This is a line that intersects. This is a single line that intersects at that point, at point B. Okay, at point B, there's one line that intersects at that one point. The slope for this line then is going to be the instantaneous velocity, because we remember we said then velocity is a slope on a position time graph, and so therefore this particular line right here, the slope of this line represents the speed the object is moving at that single point. And we can do that for any point on the line. Okay, we can do that for any point on the line. So I had asked you, could we get the instantaneous speed velocity for a point right here at about 5 seconds? And we absolutely can. What we need to do then is we need to find, I'm going to draw this real quickly, okay, the slope for that line. If we can obtain the slope for that line right there, so the slope of this line right here, the slope of this line, so the slope of that line, okay, is going to be equal to the, it's going to be equal to the velocity at that moment in time. So that this line right here that I've drawn for you right here intersects this point and only that point. So this is a line that's tangent to this particular point on this curve here. And if you do that, you can avoid having to calculate and using a little bit of calculus. So this is differentials here. So remember, velocity is the first derivative of displacement. If you have had physics, you would get that. Okay, I'm sorry, calculus, you would get that. Okay, but instead of having to calculate, and again, we set the derivative here with the limit approaching time approaching zero. Okay, so if you're interested in the calculus part of this, make sure you combine CME. We'll talk about that. But again, we don't have to do this calculation if we can just find a line and find the slope for a line that's tangent to that particular point. Okay. All right. Hopefully everyone's able to get that. Okay, so that's how we then can determine what's called the instantaneous velocity. And that's going to be more true. That's going to be more accurate depiction of an object's movement. Okay. All right. So with that said, then let me just quickly finish up here by just addressing the difference between speed and velocity. Okay. If you notice here, the speed is a scalar quantity. Speed then we can calculate for by taking the total distance and dividing that by the total time, which is very similar to how we calculate for the velocity. Remember, with the velocity, we're taking into consideration only the distance traveled from one point to another along a straight line. We're taking into consideration the shortest distance between those 2 points. That's how we define the displacement. Displacement, again, remember, final position, initial position, you take the difference between those two, and from there then you will get your, and include in the direction, and from there then you get your displacement. And so with the displacement, how we use the displacement to get the velocity, we divide that displacement by time and we get our velocity. And remember I said then the velocity and the displacement will always be in the same direction. Speed, on the other hand, is the total distance traveled over the total time. Now, if the total distance traveled is along a straight line, then speed is your velocity without the direction. Okay, so make sure you keep that in mind. But with that said, though, speed takes into account the total distance traveled. Okay, the units may be the same, the way we calculate may be the same. However, speed and velocity may not be necessarily the same, especially when objects are not moving in the same line. Along a straight line. So when you calculate for a speed here, remember we talked about this total distance traveled here is going to be 50 meters. If we were calculating for the velocity, we'd have to take into consideration the positive sign here, but we're only calculating for speed, so we only need the total distance traveled, okay, over the total time traveled, and then you get the speed then here as being 1 meter per second. If you take a look at this particular motion here, if we're calculating for the speed, okay, we only want the total distance traveled. In this case, then we do not need to worry about the direction because we just need the total distance traveled. In this case, then the distance traveled is 40 meters, okay? And the time interval that travels in is 40 seconds. So the speed here is 1 meter per second. So if you want to think about it, the speed then, if the object is moving in a straight line, the speed then is simply the absolute value of the velocity. Meaning, with speed, you don't need to worry about direction. You just the only information we obtain, the information that we obtain from speed is how fast an object is moving. What we don't know when we are given speed is the direction that the object is traveling in. Okay, so that's the key difference between speed and velocity. So again, like I said, with speed, the speed and velocity takes into account only the distance between 2 points along a straight line. So therefore, we need to know the final position and the initial position over time. Okay, whereas with the speed, we are taking into consideration the total distance traveled here. And so if you notice here, the total distance traveled, if the object is not moving in a straight line, okay, is much longer than if you were moving in a straight line. So therefore, even though the object ends up at the same position, the object takes a different pathway, and so the speed will be different for the object if it moves along the the blue line versus an object that's moving along this brown line here. Okay, so make sure you keep that in mind. Now, what will happen is that speed and velocity will oftentimes be used synonymously, but incorrectly. Okay, so make sure you keep in mind that if an object is moving along a straight line, if the object is moving along the straight line, the speed and the velocity, the number will be the same. We say then that the magnitude is the same. However, the key difference is with velocity, we have to indicate the direction. With speed, we don't have to worry about direction. Okay? And then secondly, speed takes into consideration the total distance traveled. So therefore, if the object is not moving in a straight line, it will have a different speed than its velocity. Okay? A different speed than its velocity because they are traveling, even though they start out at the same place and end at the same place, even though the object moves in the same direction, speed and velocity there will be different in terms of the number, and you won't have to worry about the sign. Okay? All right. So make sure you keep that in mind. I have reached the end of my time interval here, and so what I would like you to do then is take a look at number 4 in your problem set here. Okay. And what I'd like you to do is work out this problem on your paper, and we'll start with this problem on Monday. So work out this problem on your paper, submit it, and then we'll take a look at this problem on Monday. Okay. So I will let you know on Monday when I would like to meet live. Okay, and then I'm thinking probably Wednesday or Thursday of next week we'll meet live, but I'll let you know. And then we'll meet live on that day. I'll take whatever questions you may have, and then I'll continue on with the discussion that I left kinematics here. Okay. All right then, folks. So finish number 4 here, work it out, and then make sure you post that, and we'll start with this problem on Monday. Okay, if I don't see you this afternoon after school today, have a good weekend, and I'll see you on Monday. Okay.